Okay, so I posted a kind of startup code for assignment 1 in Canvas, and you should be able to download and access it. So you can focus on implementing that function to check for element uniqueness, and you run the code several trials as mentioned in the assignment, and tabulate the result as well as plot the result in Excel and interpret the result. Okay. Now I have extended the assignment deadline to Thursday, which is 10, this coming Thursday, and then the following assignment 2 I have extended to the following to the Thursday, which is 17th. Okay, so 10th and 17th are the updated deadline. I posted an exam 1, which is due on the following Thursday, September 24th. So I will not be extending the deadline for the other assignments. They will be due as scheduled in the syllabus. For just the first 2 assignments, I am extending the deadline to give you more time to get started with the coding. Okay. So I posted some code already for assignment 2, so that should be good enough to get you working on that. Alright, so any question on these things? Yes. Okay, so let us continue with module 2. We were looking at the merge sort algorithm. So in merge sort, what we do is split the array A into 2 subarrays B and C, sort the 2 subarrays and merge the 2 subarrays B to get the entire sorted array. So let us go through this example and understand the sequence of recursion calls that were called in merge sort. So we saw the pseudocode for these merge sort and the merge function last time, but as we go through this we'll probably see it a couple of more time. Okay, alright, so you call the merge sort code with an input array A with n elements 0 to n minus 1, and you want to really sort the array if the array size is greater than 1. If the array size is 1, it is already sorted. So check if n, which is the array size, greater than 1. Then what you do is you copy the array to 2 subarrays. So that's what I mean by splitting it into 2 subarrays. Basically you're copying. So that means the input array A stays as it is. So you're just making a copy of that into 2 subarrays B and C. So the first n over half, so 0 to n over 2 minus 1 gives you the first half of the array A. So copying that to B, and second half of the array to array C. Okay, and then you see here you are calling first merge sort on B. So that is like a recursive call because the name of this function is merge sort. So when you call merge sort on B, you go through the same process of copying again the array B into 2 subarrays. Okay, so that's what I want to show here. So this is the input array A, and you are storing that into 2 subarrays B and C, which are, say in this case 8329 and 7154, and then you call merge sort B, which is merge sort on 8329. So that means you're going to copy this array into 2 subarrays 83 and 29. So that's the second recursive call. You're calling merge sort on this, and then so that's your new that's your kind of B and C in memory for this subarray. And then what happens is again another recursive call. So remember how recursive call the function calls are getting stacked up in for the factorial problem. So that is how recursion will run. So on different portions of memory these subarrays are stored. And then what happens is this um, you're calling merge sort on this subarray with 8, 3. So that is split into two subarrays of size 1, 8 and 3. So that's the third recursive call. And then so if the array has just one element, we consider it to be sorted. So the so when you call merge sort of B on just the array with element 8 in it, it's considered sorted. So we are not going to do anything, because if you see the pseudo code, if n is greater than 1, we do all these things. Otherwise we don't do anything in this code. So that means we just return from this function of merge sort and run the following statement in the parent recursive call, which is merge sort of C on this 3, and again this is of size 1, so we don't do anything. So we return from that call. So the next line will be merge BC back to A. So that means we merge these two sorted subarrays and replace the sorted like as you merge, you replace the array A, which was split into B and C. So how we merge? So we have a pointer for the starting index for each of the two subarrays 8 and 3. In this case is only one element, so we'll be simply comparing 8 with 3. The smaller of the two gets written first, so this 8 is getting overwritten with 3, and the larger is, element will overwrite this element 3, so it is 3, 8. So 8, 3 is replaced by 3, 8. So then you see, after you merge these two subarrays and you get this one, you're done with this call of merge sort. So the parent recursive call is going to be called merge sort on this one. So then only this 2, 9 is split into two subarrays, 2 and 9. Again they are subarrays of size 1, so they are merged into so this 2, 9 is basically overwriting this subarray 2, 9. So only after you get these two sorted subarrays, you try to merge these two and overwrite the contents of this one with this one. So again you have starting pointer with at 3 and 2 and compare 3 and 2. 2 is the smaller one, so you write it here, and so you overwrite 8 with 2. So that's why I show the arrow to indicate that you're overwriting this array with the sorted as a sorted subarray. Then move the pointer here, compare 3 with 9. 3 is smaller, so move the pointer now to this one, compare 8 with 9. 8 is smaller, and then write the 9. So only after you generate this sorted subarray, so you see it's going as deep as possible, and then you start merging. So this is equivalent to calling merge sort of B on 8, 3 to 9, and you have really merge sorted it. And then now you call merge sort on C, which is the 7, 1, 5, 4, and you go through the sorting process. So you split this into 7, 1 and 5, 4, then focus on the left subarray, which is 7, 1, split it into 7, 1. These are subarrays of size 1, so merge them, it becomes 1, 7, and then split 5, 4 to 5, 4, and then merge them to 4, 5, and then combine these two subarrays, you get 1, 4, 5, 7. So you can see the numbers indicate the order in which you execute the sorting process. Okay, that's the sequence in which the recursion calls happen. And now these are the two sorted subarrays B and C of the parent array, which is this one A, and then you merge these two sorted subarrays. So we went through the course process last time. So you start with again the first element at each subarray, 2 and 1 in this case. So 1 is smaller, so overwrite this 8 with 1, then move the pointer to this element, it is at 4, compare 2 with 4. 2 is smaller, so write down here and move the pointer to the next element. So compare 3 with 4, 3 is smaller, so then move to the next element. 8 with 4, 4 is smaller, so move it to the next element. 8 with 5, 5 is smaller, move it to 7. 8 with 7, 7 is smaller, write down. So you're done with this subarray. So now you can write down the contents of the remaining contents of the left subarray in the parent array, overwriting 5 and 4 with 8 and 9. Okay, so at the end of the process, the input array does get changed. It it is overwritten with the sorted data values. But you see, as part of the process, you're still using additional memory that is proportional to the input size. Okay. So that's why the space complexity of merge sort is theta of n. Okay. Any questions so far? And we'll now go to the time complexity. But any questions? Alright, so let us do the time complexity of merge sort. So this is divide and conquer, and we saw the general recursive relation, that is the time to solve a problem of size n. You are splitting that into sub problems, each of size n over b. And solving a of those sub problems plus the time to merge the solutions that is spent to merge the solutions. Now here, so again, coming to the basic of time complexity, we need to find what is called the basic operation that is repeatedly done as part of the algorithm. So we are not doing any operation really here, we are just copying the elements and then recursively calling merge sort. So only in the merge function we are doing things repeatedly, which is this comparison operation and then merging. So we can indicate the analysis in terms of finding what's called the number of comparisons we have to do to sort an array of size n. So what we do in the merge sort is we are splitting that into two subarrays of size n over 2, and so let us indicate C of n over 2 as the number of comparisons you do to sort a subarray of size n over 2, and you are sorting both the subarrays, right? So this is an array of size n, you are splitting that into two subarrays of size n over 2 each, and you are going through this process to sort this subarray of size n over 2 and another subarray of size n over 2. So that is 2 times the number of comparisons to sort an array subarray of size n over 2, because you are solving both the sub problems. That's what it is. And then you are spending time to merge the solutions of the two sub problems, which is the two sorted subarrays in this case. So you are splitting that into two subarrays and going to C of n over 2 number of comparisons to sort this subarray, and another C of n over 2 comparisons to sort this subarray. So that's why it's 2 times C of n over 2 to sort the two subarrays. And then you are merging the two sorted subarrays to get the original array sorted. Okay. So what we need to do now is find how many comparisons we are doing to merge two sorted subarrays of size n over 2 and get and generate a sorted array of size n. Okay, so that's what we need to. So this is a recurrence for n greater than 1. So again, as I said, you need to sort an array only if it has more than one element in it. If it has only one element in it, you don't need to do any comparison. The array is already sorted. So the number of comparisons to do if there's only one element, which is C of 1, is 0. So the kind of unknown in the sense it's not clear right now, what is the number of comparisons we have to do to merge two sorted subarrays of size n over 2 and get a sorted array of size n. So we have to decide whether we do the same number of comparisons all the time or not. Okay. Now, if you look at it, so we go through some comparison, right? So we compare 2 with 1 and then decide 1 is smaller and write down 1, and then compare 2 with 4, decide 2 is smaller, write down 2, and then compare 3 with 4 and so on. So those are the comparisons I'm talking about. So is there any difference in the number of comparisons we'll be doing for any array of size n over 2 each? as I have indicated, it is yes, is a best case and worst case. So let's look at the best case scenario. So best case is if the two sorted subarrays look something like this. So this is one sorted subarray and this is another sorted subarray. So if you are merging these two sorted subarrays to get the final sorted array, what we'll be doing is starting with 1 and 5, the two subarrays. So 1 compared with 5, 1 is smaller, so we'll write down 1. Then so you move the pointer to the next element, 2 compared with 5, 2 is smaller, so write down 2. Then compare 3 with 5, write down 3, and then 4 with 5, write down 4. So now we are done with this left subarray, and as per our process, we simply copy the remaining contents of the right subarray, which is this entire array, to this final sorted array. So we'll write 5, 6, 7, 8. So if you think about the number of comparisons, we are doing actually one comparison for each element in this left subarray with the first element in the right subarray. So the number of comparisons we will be doing in this case is simply 4 comparisons comparing to corresponding to the size of the left subarray, which is n over 2. So in general it is n over 2 comparisons. That's the best case. Now the worst case scenario would be if you have to do more than this, which will correspond to the two sorted subarrays being something like this. So if you think about merging these two sorted subarrays, what we'll be doing is comparing 1 with 2, 1 is smaller, and then so that is one comparison, and then compare 3 with 2, 2 is smaller, so write down 2, and that is another comparison. Let me indicate that here. And then 3 with 4, that is one comparison, so 3 comparisons so far. Then 4 with 5, 4 is smaller, so write down 4, so that is another comparison. Then 5 with 6, so 5 is smaller, so that is one comparison. Then 7 with 6, that is one comparison, with 6 being smaller. Then 7 with 8, that is one comparison, 7 being smaller. So once we are done with the left subarray, we can now write the remaining portion of the right subarray as usual, but in this case it's just the last element 8 out there. So if you look at the process, we are doing really what is called n minus 1 comparisons to generate the sorted subarray of array of size n. We are doing n minus 1 comparisons. So that's the worst case. So the best case is of course different from worst case, is n over 2 and n minus 1, but if you again think in terms of the asymptotic time complexity, again asymptotic means you will focus on what happens if n increases, n grows larger to infinity. So as n grows larger to infinity, you have to look at these two functions, n over 2 and n minus 1. So this function, again, if you want to analyze in terms of asymptotic time complexity, the policy we follow so far is discard the lower order terms and discard the coefficient, if any, for the most dominating term. So for n over 2, there is no lower order term, it's just one term, and the coefficient of this term, which is half, should be discarded as n grows larger. That's not a significant thing to look at. So as n increases, n over 2 can be approximated to n. Even though it's half, it's still a function of n. It's not like function of n square as n increases, right? So it still grows as a function of n. Now again, n minus 1, as n increases, the 1 can be discarded, and there's no coefficient for n, so it is also grows as a function of n. So what we can say is, as n increases asymptotically, as that's what it means, it's both are functions of n, right? So we can say that merge function, the merge process, is theta of n. So that's what I have indicated here. So the merging time complexity, this merge time, is theta of n. So we can now write the recurrence relation as C of n is 2 times C of n over 2 plus theta of n for n greater than 1 and C of 1 equals 0. So you can solve this using master theorem by finding out the a, b, d values. So again, the general format is T of n is a times T of n over b plus theta of n raised to d. So d is 1, a is 2, b is also 2. So once you identify a, b, d, the next step is to evaluate b raised to d, which in this case is 2 raised to 1, and a is 2. So 2 equals 2 raised to 1, which is true. So a equals b raised to d. So if a equals b raised to d, so there are three formulas I gave you for master theorem, depending on whether a is less than b raised to d, a equals b raised to d, and a is greater than b raised to d. So in this case, a equals b raised to d. So the formula is, the time complexity is theta of n raised to d log n. So here d is 1. So we can say it is theta of n log n. So this is the time complexity of merge sort. Okay. Now, if you think about the time complexity of the sorting algorithms that we have seen so far, which are like insertion sort, bubble sort, or selection sort that we saw in data structures, all of these are either big O of n square or theta of n square algorithms. So they are n square time complexity algorithms. Whereas merge sort that we saw now is n log n, theta of n log n. Okay. So n log n is smaller than n square. So that means the time complexity of merge sort is less than the sorting algorithms I have put here, the insertion sort, bubble sort, selection sort, and all this stuff. On the other hand, the space complexity of these algorithms here is theta of 1. So if you remember, we saw insertion sort and bubble sort in this course. They don't require any additional space. You just work on the input array itself. Of course, use some temporary variables, but again, the number of temporary variables you use doesn't grow with input size. It's always the same irrespective of the input size in these sorting algorithms. So we can say these algorithms, insertion sort, bubble sort, and selection sort, are in place in nature because they require theta of 1 space complexity, and we saw about in place in separate slide in detail before. Whereas for merge sort, we cannot say it is in place because its memory requirements grow with input size. So if you think about what we did, so we are copying the input array A into two subarrays B and C. So if the input array has n elements in it, you need another n elements or memory space for the two subarrays B and C. Of course, you then go through the sorting process, merge them, and so on. So, but still, it requires n additional elements or memories for n more elements. If you want to sort n elements, you have to allocate n elements for the input array as well as n more elements for the two subarrays B and C. So its space complexity is theta of n because you need n additional memory. So we can call this as a space-time trade-off. If you want to minimize the time, you go for merge sort with n log n time complexity, but you have to spend additional space, which is theta of n complexity. Whereas if you are okay with the time and you do not want to use any additional space, then you go for insertion sort, bubble sort, or selection sorting on these algorithms. And among these, insertion sort is probably more relatively less time consuming compared to bubble sort and selection sort. Okay, I may give you a comparison based assignment of comparing 2 or 3 sorting algorithms. I'm still thinking about it. Okay. Uh, but you will encounter, as I said, n square time complexity. So that's why it says space-time trade-off. But you may wonder, is always there a space-time trade-off in sorting algorithms? The answer is no. There's an algorithm called heap sort that we also saw in data structures. It doesn't require an additional space. If you remember about heap, you don't need to really create the binary tree and all this stuff. You can process the array input array itself as a heap if you rearrange the contents to satisfy the heap property. Okay. So the heap sort algorithm is n log n, like merge sort time complexity, and its space complexity is also theta of 1. So it brings the best of the two. So it's both time as well as space efficient. So if you want to pick the best sorting algorithm, then heap sort is probably the best because you don't have to spend additional space and still get n log n complexity. Whereas merge sort, you have to use additional space, theta of n space complexity to get time complexity of n log n. Okay. Any question? Okay, so let me save this and then we'll